Okay, everybody, there are still people joining in, but this is just an introduction. So first of all, I'd like to welcome everybody to the second talk on the Minitutorial on deep learning and for inverse problems and partial differential equations. As I posted in the chat line, the presentation is recorded and will be available on the SciEM homepage for the conference at the YouTube channel. The speaker today is Eldad Haber, who will be talking about deep neural nets meets ODEs and PDEs. Eldad is an expert in the field of computational inverse problems and applications in machine learning, and has also a background, if I'm not wrong, from geosciences, which I think you're still active in, but also doing a lot of other stuff related to computational sciences and inverse problems. He is currently professor at the Department of Earth, Ocean, and Atmospheric Sciences at the University of British Columbia, and he's also the chairholder at the Natural Sciences and Engineering Research Council of Canada. He's written many software packages that actually have been used also in industry, which is unusual for academic research. He's co-authored a wide range of papers, about 150, in these fields that are quite broad. And he was also an early career award recipient of the US Department of Energy. He did his PhD in '98 at the University of Columbia, British Columbia, sorry. And then he essentially he actually worked a couple of years in industry as a research scientist in Schlumberger, and then he moved to the Emory University in Atlanta, where he essentially returned back to the academia. During his journeys, he has at least co-founded 2 companies that I know about. One in 2011, Computational Geosciences Incorporated, and one in 2017, Extract AI. And both companies seem to be doing well, at least from the homepage. Returning to the science part, I think that, bearing in mind the title of the slides, I think it will be on the work that he's been doing with Lars Toto and perhaps Eran Triester. And you could say that that's work kind of started, at least the first publications came out in 2017. And the overall goal, to my understanding, was to investigate properties, stability and robustness, and perhaps even explainability of deep neural networks from the point of view of seeing them as dynamical systems governed by ODEs or PDEs. So essentially time represents the layers in that context. And before I leave over to Eldad, I also want to mention that he's also done work on medical image registration and optimal mass transport, again with people that are prominent in the field, like Alan Tannenbaum and John Modetsky. With that introduction, I leave the word to you, Eldad, please, and I will mute myself. And I think the best, from a practical point of view, is that we take the questions at the end. If there is a very, very urgent question, you could raise your digital hand and I might try to attend to you then. And that was for the attendees in general. Okay, because the attendees are muted. So thank you very much, Eldad, and the floor is yours.
Thank you very much, Orson, for the elaborate introduction. This is a tutorial, so I'll try to not dive amazingly deep into any type of theory, but try to give kind of an overview of things. With the idea that we want to kind of dive maybe later in, there is some kind of a small page that is on GitHub to share a little bit about software. I'll try to show it at some point. If my computer just crashed before this, so I hope everything is still working on this thing. But if not, I'll just point to the thing, and then at the end there's going to be another pointing to another project we're doing right now, which involve COVID. As Uzan said, the work, why is it double page? I don't know. It's a good question. You see 2 pages or 1 page? 2, okay, we'll work with this, it's fine. So the work here was not done only by myself. There is a team of people. I'm just going to put the 4 more recent ones. Lars is, of course, started the journey with me on looking at the deep neural network as ODEs. And then Eran joined shortly after as a postdoc. Keegan is a student that's currently working on projects right now. And Bas is a visiting scientist / postdoc, was here working on, again, on deep network with applications and some things here. What we're going to talk about is going to be about deep neural networks. And then what we're going to talk about how they, the connection between deep neural networks and ODEs, and this will suggest how we are going to be able to look at new architectures for deep neural networks. And the next thing after that is we'll talk about how we can actually combine it with PDEs and suggest architecture for this. I will talk a little bit about applications. In particular, I'll talk about a typical application right now is we're looking at lung CTs and how to diagnose corona patients with lung CTs with a joint project with Vancouver General Hospital. So I'll talk a little bit about this and then maybe conclusions a little bit. So that's a plan. You know what, I will try to do this. It's better, even though we have to maybe manually do some things here. Okay, so let's talk first about what do we have here. We have the usual machine learning applications, which everybody knows, like for example, image classification. When you're giving a small image, this is example from data called CFAR10. When you're giving an image and you have to classify it to a certain class, this data set particularly is actually very low resolution. It was done in early days when computers cannot really deal with very high resolution, or so this is 32 by 32 images, and there are 10 classes. And this particular data set actually led to quite a lot of research papers. Initially, before the deep learning, people could get only something like 60-something% accuracy on this, and today the papers suggest that people can get with deep learning to the accuracy of 90+%. I can tell you that trying this partially on 3 hungry kids with ice cream, you can get to around 90% as well. So the result is that you can, people say you can get to more accuracy that is better than human on this thing. So this is one task. You take an image and you return a label. You return what it is, a car, a truck, or whatever it is. The second one is semantic segmentation. In semantic segmentation, the goal is a little bit different, and I would like to differentiate between the two. Later on, you'll see also why. Is unlike before, when you're giving the whole image one label, you're in essence compressing the information in the image. Here, you're actually giving every pixel what its meaning. So you're doing segmentation. The usual thing is segmentation, but semantic means you're actually giving it a meaning. So you're saying that, for example, this thing is a different color, is a car, and this thing is a crosswalk, and so on. The important thing to remember that even though we start from one image and we think we get one map, we actually get a number of maps. The maps we're getting is the probability of each pixel to belong to a certain class. And we'll talk about this particular task later on in the talk. So this semantic segmentation, again, you're going with something which starts at the size of an image and ending with something which is the same size of the image. So information is compressed a little bit, but actually not by much, because again, each pixel there's multiple classes for each pixel. So this is something to remember. In applications, for example, that Bas was doing, you can actually extend these things to fields like seismic, where you're going to take a seismic image and come with what we call semantic segmentation, in this case for the image, which is telling you what layers you have in the seismic image. And we'll see an application to medical imaging towards the end of the call. So there are different types of application for these things. Now, what are deep networks? Again, people that are in here probably know most about it. These are neural networks with a particular structure, so they're very deep, they're very long. They exist for a very long time, so it's not really a new thing. I mean, the whole thing exists for quite some time, but only in the last few kind of 10 years, people managed to train them efficiently and managed to do very efficient things with them. And of course, there are many applications which are supposed to really do the things like image classification. We talk face recognition, driverless cars, more and more. One of the things that people like to do is to quote, find these quotes. And every time I do this talk, I need to find a new quote that is done recently in the newspapers. I think, of course, everybody wants to know that data scientist is the sexiest job of the 21st century. So that's why everybody wants to go and do these things now. And courses in the university, for those of us who are teaching at the university, are exploding with undergrads that are looking at these kind of job opportunities and other things. So there is definitely a hype about trying to understand what's going on in this field. The problem with this field, though, that again, the engineering seems to be doing not too badly, and we have a lot of solutions for problems, but we don't really understand what we're doing in many cases. I mean, there is definitely a surge of papers that is trying to understand why this thing is working so well. Why we're stuck on the 60-something%, or in semantic segmentation, doing some things with partial success. And this is can be so successful, can be also failing when we do things. So we're trying to understand, what are we building? Why does it work so well? And this is still something that is not completely understood. There is a lot of gaps to find out here, but this is one of the things that we're aiming a little bit to do in this work, not guaranteeing that we're getting to the point we understand exactly why it works, but trying to bring the deep learning into what we call the standard science that we're doing. So here's how usually data scientists plot machine learning or deep network for me. When they say there is some input sensory, there are some input layers that are so input layers, there are hidden layers, and then there's going to other things. When people start to do this to me, especially my students, I tell them, forget about it. I don't want to see this anymore. I want to see this, because we invented in math, this thing that tells you input, and the connection between them tells you to have weights. This is exactly a matrix vector product. So we invented matrix vector products exactly for this goal, to avoid plotting dots on screens. And it's not just we don't want to plot dots on screen. Matrices have properties. Matrices can be symmetric, anti-symmetric. They have eigenvalues, they have eigenvectors. These things mean something for some of us. And the thing is that it will tell us how networks actually behave. So when we plot something like this, it's maybe good graphically for the general public, but from a scientific point of view, we should really think about it from a point of view of a matrix vector. Even though when you talk about convolution neural network later on, you should think about not the convolution as the 3x3 or whatever it is object. You should think about it as the matrix that multiply the vector on the side, because this matrix is going to really give us what this thing is doing for us. So this is really the way we should start thinking these kind of things, and that's this is the kind of the start of where I want to kind of take us here. What we're going to focus is we're going to focus on the structures called ResNet, so residual network. This was pioneered by a group from Microsoft in 2015. And what they said is, they said that rather than looking at a previous one, which looks like this, so I have y is equal to some activation function of a matrix times the previous y plus b, what we're going to have is we're going to have y in the next version, next layer is going to be equal to the y in the previous version, plus basically a function that looks like this. You multiply the previous, the current layer by matrix. You add some vector, which is usually a constant vector. You take a nonlinearity and you multiply by another matrix. We added a small h here, but we say, okay, let's start with this one. Doesn't really matter. Later on, we change it, but it comes into the h, into the k anyway, so it doesn't really matter. And this is the structure they have used, and they won a number of competitions at the time and showed that you can do quite amazing thing with particular structure. So the idea is that you propagate with this thing until you get to the end, and then you do classification by multiplying it with another W, the final layer, and get something which is called C, and you can do stuff with it. You can, for example, do classification, segmentation, whatever you want to do with the structure that you have. Okay, so here is the kind of the structure. You propagate. Just to kind of put things, these are the weights that are going to use for the propagation. And in the forward problem, all you want to do is to propagate forward. So you're assuming you know these Ks, you know the nonlinear activation, you know the bias, and I'm giving you some data y0 and the y or y1, depends on your MATLAB or a Python user. And this thing goes in, and as it goes in, it goes through all the layers, it gets you the end, and then at the end you multiply it by the W, and then it classifies it for you. So that's the forward mapping, and that's assumed that that's what you can do. And this is of course done after the network is trained. So if you think about Siri on your iPhone, somebody have trained all these weights. You're asking a question, it comes into as this kind of vector. It runs through the forward process and gives you back the answer you want to get. So that's in the forward problem. In the inverse problem, you're not knowing you don't know what these K's at all, or B or W, and what you do is you're giving the data, and now you are trying to train the network. And this is done as usual we do in inverse problem. You design a loss function. So you design some function you want to minimize. Typically, if you're looking at classification, it's going to be something like cross entropy. And then what you do is you solve this optimization problem subject to fitting the thing. You can add regularization. As you'll see later on, you can do different type of regularization. One of the amazing things about machine learning is that people invent new words all the time for things that we know. For example, Tikhonov regularization is called weight decay. So if you're just doing Tikhonov regularization, when you're minimizing over the weights, you'll see people call it weight decay. But you can do more sophisticated one, and we will talk about particular one or two extra regularization you can do. Of course, this problem is highly nonlinear. So there is usual, can be instability, can be lack of generalization, can be many local solutions, and the question of robustness always come by. Okay. So one of the first thing we did when we looked at this, we said, this looks, when you look at the structure of a resonate, you say, this looks a lot like a forward Euler discretization of a simple ODE. And the nice thing is that you're moving from a discrete to a continuous process, that it allows you to do a lot of things, as we'll talk in a second about even from an interpretation point of view, where you're saying, okay, I can now move from this particular description to this description. So looking rather than yj plus 1 is equal to yj plus, you say, let's look at the time derivative of y, where time is a fake variable we invented, is equal to that function. And the advantage of doing something like this will be that we can now, for example, decide, like before we say, we don't know how many layers we should do, 30 or 60, you can think that this is the same as discretizing an ODE with as many time steps as you need. And you can start thinking about adaptive methods, you can think about theoretical aspects of the solution. So there's a lot of other things that are interesting. So a bunch of us came with the idea at around the same time. Wayne and E came with the same time. About a year later, people in Toronto coined the term neural ODE for this thing. And since then, actually, quite a lot of people have been looking at this particular thing. And it's kind of an interesting idea in some way. Now, let me just show you a YouTube thing that is on, like, kind of we put online for this. So you can think about this in this way. Let's say that I want to classify these points into classes. So you see there's like 5 classes in this particular example. In order for me to classify these points, in principle, if I want to use linear classification, because we multiply by W at the end, I can't do this because everything is here highly nonlinear. I mean, as you can see, I mean, you have this red class or whatever, purple class, which is here, sorry, purple class here, here, and here. And these things are not together, so I can't find a linear classification that will just do this right. But if I use these dynamics that we just introduced, then you can think about every layer as a time sequence, and you see this thing is just going. And at some point, it's just organized to a point that it can go again, and I'll just kind of show you how it's doing something. So that's the way we view this kind of networks. There are some interesting questions people always ask. For example, you see this is kind of doing almost, it's a typical graduate student doing nothing, or a little, and towards the end tends to organize. So why is that? And again, you can come up with different ideas to shorten that particular distance. I'm not going to talk about this right now, but that's the view. The view is you have a dynamics that takes you from layer to layer to layer to layer, and eventually you can go ahead and say, now I can do a linear classifier. So the W that I have at the end multiplies it, and I can just separate these things with just simple lines. And that's the way this is done. And this is done, of course, this particular demonstration is done by training actually a network to do this. Okay. So that's the basic idea behind it. Let me go to the next one. So those of us who, so again, as Uzan said, I've been doing inverse problem for some time. And typically when you do an inverse problem and you start with a forward problem, and the forward problem, for example, I did a lot of work on electromagnetics, you ask yourself, is the forward problem well posed? And typically, of course, it is, because it's a physical process. And it's very important to work on inverse problem that the forward problem is well posed. So remember, inverse problem typically are ill posed, but the forward problem is, actually, I don't know any forward problem that is not well posed. And usually people have done this work for us. So talking Maxwell's equations or Navier-Stokes equations, or people have proved these kind of things for us. Here, we realize that we have a neural network, so we have an ODE, but nobody really asked the question, is this ODE well posed? How are we solving an inverse problem where the forward problem is not well posed is not such a good idea. And in a second, we'll see why. So you can ask yourself first, is the ODE well posed? And the question that you can ask yourself, is the discrete ODE well posed? So, well, why do you want to have something well posed in the forward problem is a very simple thing. I mean, if you think about the classification problem, if you take the classification problem and add a little bit of noise, you want that the class at the end of the day will stay about the same. So that's basically what well-posedness means in a very simple term. So you want that if you perturb a little bit the initial condition, you can think that if you recorded something, you classify this as a bare, you want after you add a little bit of noise to the image, this will be classified as a bare as well. Well, this is known to be a problem of deep learning, which is obviously ill-posedness. People are doing it with what they call adversarial example. It's a little bit not, it's not as benign as what I'm, or as bad as sometimes that people present it, because these are adversarial examples. It's not just noise, it's noise that is designed to do the worst case possible, but still it's ill-posedness. You're looking at an image of a panda bear, you're adding a little bit of a noise, like a really little bit of a noise, and then you're getting that this thing becomes a monkey. So clearly the machine learning system went very far, and this is a prime example of ill-posedness as we see it. So this is something that we should not have for a system that we would like to have, and this is caused by the ill-posedness of the forward problem, not the inverse problem. So the question is things are well-posed? And the answer is definitely not. I mean, why should they be? No, this is not a physical process. This is machine learning. We can do whatever we want, and I'll get back to we can do whatever we want a little bit later. I tell my students all the time that the difference between machine learning and anybody who've done work on any other inverse problems, that in inverse problems, if you work on Maxwell's equations, you're stuck with Maxwell's equations. If you're working with fluid flow, you're stuck with fluid flow, and you're stuck with, you know, Navier-Stokes equations. In deep learning, if you don't like the model, you just replace it. There is no problem to just change the model. But in general, in this case, most DNNs are not well-posed. So you can open books on these things and find out what does it mean to be well-posed, and we'll go in a second what you need to do for this. But there's some things you can do. You can basically try to put weights on constraints on the weight matrices, and you can design networks that have better structures and better architectures. So, and that will make the discrete dynamics well-posed. So let me go over this thing very quickly. This is coming from ODE books. And I'm a little bit cheating here. Basically, you look at y prime is equal f of y, that's an ODE, and you look at the real part of the eigenvalues. And if the Jacobian is, if the real part of the Jacobian is positive, you know that you have locally exploding terms there. It's a little bit, this is assuming the Jacobian is changing slowly. If you want to look at something a little bit more accurate, then you should look at something which is called kinematic eigenvalues. There is a book that Uri Asher published in '84 these things and discussed this thing quite deep. But again, I mean, if you think the Jacobians are changing slowly, you can look at the real part of the eigenvalues. And again, I mean, if you look now at our Jacobian, it's made with a matrix that operates we chose. It's a diagonal of this nonlinear function that we chose, which usually goes between 0 and 1 times another matrix. There is nothing that guarantees that combination of these two matrices will have non-positive eigenvalues, the real part of the eigenvalues. So nothing guarantees that this is going to be well-posed, at least for all the layers. So in principle, there is nothing that tells us that things should be well-posed and things should be pretty bad. Now, what can you do? You say, well, I mean, I can do a bunch of different things. I can, for example, choose the K2 to be equal to identity. So if I look at this thing, if this is identity, this is a diagonal matrix which have entries that are all bigger than 1. So if this one have eigenvalues that are imaginary, everything will be fine. You can do that. That's kind of easy. So here are two solutions for this. One of them, you just say, I'm going to look at something which looks like, again, K2 is identity. This is A minus A transpose, so this antisymmetric, so all the eigenvalues are imaginary. And the ODE is going to be fine here in this case. Another one which we found a little bit more useful is this one, where, to be honest, we found out later that other people have done similar work to this. They came to this from a very different perspective. I'll come to this later as well, where you introduce another demi-variable, which we call Z. And this is coming similar to what we do in Hamiltonian networks. And now you see that Y depends on Z and Z depends on Y. And that's the typical way to do this. This will also have purely imaginary eigenvalues, so for these particular things. So this is an ODE that has only imaginary eigenvalues, and it's stable and it runs very, very well. The problem is that if you discretize it, if I take this and discretize it with forward Euler, which is a particular discretization of what we're doing, then nothing good will happen because we teach these things all the time. This is going to be unconditionally unstable because the forward Euler ball of convergence is here, and these are all imaginary eigenvalues, which are on this axis over here. So you can come up with crazy discretization. We never use this discretization, but I like to show it every time in a talk because My claim is that if you never thought about ODEs, you would never think on weights that looks like 23/12 and 16. I mean, the yn plus 1 is equal yn plus something. That kind of makes sense. But this thing with all the previous layers don't make any sense if you don't think about it as ODE. And this is actually stable, much more stable for these kind of things, as people know from ODEs, and it can be worked quite nicely. So this is kind of the things that is worthwhile looking at. For the one that is a Miltonian, you can do Varlet methods where you take the y as a function of z, then updating the z, you go to the y, and vice versa. So this is, again, this is the discretization we're using here. It's what's symplectic discretization. It has some very nice properties for those of you who are into ODEs. Again, there are lots of ODE integrators. People have used recently Runge-Kutta methods and other things, but of course they should fit to whatever you're using. And I'll talk a little bit about implicit methods later on as well, because they have some role here. Okay. Now a few comments on this thing. So since this whole idea came through of ODEs, people forgot discussions we had in the PDE ODE optimization community about discretize and optimize. So the idea is this: if I want to minimize some function, doesn't matter right now which one, subject to an ODE, I have two options. One is I first write the, I first discretize the ODE, sorry, first. So for example, I can use forward Euler and then just treat the problem in discrete form. The other one is I can write the condition for optimization in infinite dimension for the y, so in continuous time, and then differentiate the equations in continuous time, and then do the discretization later. This is called OD. In the world of PDE optimization, which we work on many, is most people would prefer the first approach because it keeps some very nice properties. There's some summaries, for example, in a book by Gunsberger on control of flows that summarize some of these things. Here's an example to why we prefer to discretize first and optimize later. So let's say we take a very simple problem of fitting basically the end condition to a number, and we have a very simple ODE, and the parameter we want to evaluate is the initial condition. So it's not exactly deep networks, but the same idea behind it. In this case, you can write the Lagrangian, and this is what would happen if you want to first optimize and then discretize. So you write the Lagrangian in continuous space, and then you differentiate the Lagrangian and get the optimality conditions. And these are the optimality conditions. So you get basically the forward problem as usual, and then you get the adjoint here, which what we call back propagation, which propagates from this for the Lagrange multiplier, you propagate back. The problem is that, for example, if I use a forward Euler or forward Euler for this with non-uniform time steps and something non-uniform time steps here, these two equations are not going to be adjoints of each other. These are just, you can think about it as a linear operator on y and a linear operator on u. These operators are adjoints in the continuous space, but they're not going to be adjoint in the discrete space. And that may lead to things, for example, that the discrete gradient may not actually be the continuous gradient. They would differ, and they can differ quite by a lot. And then you find yourself not minimizing the function you want to minimize. So this is a little bit of subtlety here, but this is why clearly if you solve the ODEs to a very high accuracy, problems are usually avoided. But what we're trying to do most of the time in computational science is to avoid very, very high accuracy, and especially in these kind of things. So that's why the idea that some people have in this field that they want to first do this and then go ahead and look at the conditions can fail quite miserably. And again, the recommendation that we have that for most problems, you should discretize the problem first and then optimize. Okay. I'm going quickly because I want to look at the other things we're doing here. So in the optimization, again, I'm not going to invent anything new here. Really, we're using stochastic gradient descent. Stochastic gradient descent, we're using back propagation. Back propagation is basically the adjoint. It's actually quite amazing, again, how people invented back propagation without knowing that the adjoint exists. It's basically the same process exactly. So it's nothing else. Now, last thing, maybe last slide to try to convince you why you should care about stability. So just trying to do something very, very simple here to show, because we want to plot how the landscape of the objective function looks. So what we do here is one of my students did this actually, when we looked at what happened when k is constant. So it's just going to be a matrix, and this is going to be a nice matrix. You can see that you can look at the structure of the matrix. There's nothing really that suspicious about this particular matrix. And what we did is we just look at this particular structure, which is also a nice structure, relatively speaking here. And what you do is what happens when you take H to be, so again, the question would be, what is more nonlinear? A network with lots of layers or a network with less layers? So what we did is we integrated from 0 to 10 with layers at H is equal 0.5. So that's 20 layers. Then we did the same thing with 200 layers. And we look at this function here, which is just a function of theta 1 and theta 2, because now it depends only on two parameters. So 20 layers, 200 layers. And the 20 layers, we lose stability of the ODE here. And when you lose stability, this is how the objective function looks like. You use 200 layers, the same ODE, just 200 layers, and this is how the objective function looks like. So clearly, looking at more layers is not making the problem more nonlinear. It's actually the opposite. Having more layers makes the problem more linear if you're keeping this H smaller and stability resumes. So again, it's also not just that it's stable from a point of view of the forward problem, it's also good for the optimization later on, because minimizing something like this, I think people would agree that is much better than minimizing something like this. So again, one of the other reasons to think about keeping stability. I will actually shorten this one, and there is a Jupyter notebook which I'm not going to go over right now. I thought maybe I have more time, which I made for this particular thing, where we're just recovering this very simple ODE approach and training and doing all these kind of things. So people that are interested can just look at this particular Jupyter notebooks for this. It's using PyTorch and just give a demonstration for the concept we're kind of talking about. So I have about 15, 14 minutes. I would like to kind of go to convolution neural networks and talk a little bit about more sophisticated things as we're going to higher dimensions and talking about images. So we go to the same idea as we did before. And the only difference is that now the Ks are not going to be dense matrices. They're going to be what we call convolution. So they're convolution, which means you can think about it as periodic matrices that have a certain structure, usually some kind of toplet structure. And of course, you can compute them very quickly by computer software, which was written specifically for that. But that's the only difference. So you can think about Y as an image, K is a convolution, sigma nonlinearity, another convolution, and so on. Okay. So when you look at convolution, you have to start thinking that maybe there is a connection to PDEs. And the way to think about it is this. If I have a convolution in one dimension, which is the easiest thing to demonstrate, that is made of 3 numbers, so it's a 3 by 1 convolution, or 1 by 3 convolution that convolve with this particular vector, I can just represent this convolution with a different stencil. Rather than K1, K2, K3, I can think about it as something else that operates on Y, which is S times the convolution 0, 1, 0, S2 divided by 2H with minus 1, 0, 1, and S3 divided by H square, 1 minus 2, 1. And there is a one-to-one mapping between the Ks and the S's. So if you think about the convolution in this way, you can think about a continuous operator that looks like this: S1 times Y, S2 dy dx, S3 d square Y to dx square. So the convolution is really, you can think about it as a discretization of a PDE rather than ODE in this case, and on a grid, on a particular grid function. Okay. And again, this is useful because now you can think about all these things as convolution models, as PDEs. And now you can start mapping some of these things toward PDEs that we know. For example, if you look at the model that people have been using, and you will choose this K2 to be K1 transpose, then you recover a parabolic PDE. And you can think, and you can actually look at this thing furthermore and look at how it's doing for image segmentation, for example, and realize that this is an extension of things like total variation based segmentation or Mumford-Sachs segmentation, where you're using some kind of, in the typical things, there will be a gradient over here, there'll be a nonlinear function over here, and a divergence over here. So rather than having a gradient, you say, I'm going to learn the operator, and it can be much more free than just choosing a gradient, for example, with Mumford-Sachs, for example. So again, you can think about it as anisotropic diffusion, which was very, very successful for, again, a lot of problems. And you can basically learn the operators that you want to learn for the segmentation problem. Okay. Early days of this, in 2017, we were very excited. We did work on STL10. With this approach, we managed to get better results than the results that were at the time. So we got very excited by this. I think by now, again, these things, every competition, every conference, somebody breaks immediately your, it's kind of like the Olympic record. Everybody break it in another 0.5% or something. But in 2017, we felt that we had something really good in our hand. But now I think everybody gets to like 90% in these data sets. So it's not as impressive anymore. But the interesting thing for us came later, and this is work that we've been doing with both Keegan and Bas more recently. So if you look at the current model where you have a derivative of y is equal sigma of y and theta, so some nonlinearity here, you can think about this as, people say this is supposed to look like networks, but I would say it doesn't look at all like physical networks, because these things are, in general, they're lossy. So if you think about networks, this should not be really representing networks, although this is the most simple description of a network that we think about. If you think about a physical network, if you think about, for example, things on a wire, or think about your nerve system, which is also moving over some kind of a biological wire, then things are not lossy and they're reversible. So it means that information can go both ways. This is not the typical things that happen for a deep neural network. So what is the right model for this? Well, those of you who knows a little bit of history, this is a telegraph, one of the first ones. And really what a better model for these things is really thinking about a second order equation. So this is a nonlinear telegraph equation. You can think about it as so, which means that we're using second derivatives and not first derivatives. And this is really a more appropriate, I mean, if you do believe, again, I'm not a big believer that neural networks are really connected to neurons in our brain, but if you do believe that there is a connection between neural networks and real neurons, second order equation describes the whole thing much better than the first order equation, because second order equation really talks about propagation of information over networks. And if you start with this particular model, then you get up a completely different network with very, very different properties. So again, remember what I said in the beginning, if you don't like your equations, just change it. And at some point we didn't like this equation because we wanted different properties. We want to conserve information, so we changed it. We just added another derivative. What you do is it immediately kind of comes to, if this is the model, to a leapfrog discretization, which is classical discretization for everybody who's done second order equations. And this is what you're getting. The nice thing about it is a reversible transformation. So if you know yj and yj minus 1, you can get yj plus 1. On the other hand, if you're going from the end and you know yj and yj plus 1, you can just take this thing to the other side and you know yj minus 1. So information goes from one way to the other and back. And this actually has quite a lot of consequences in terms of memory, for you have to save. I'm not going to go into this, but you can design networks that you don't have to store activations as you're doing the things in the middle. So that's the one thing. But again, you're saving information, which may be important for some applications. Another thing is that you say, wait a minute, if we know PDEs, in PDEs we use a lot of implicit methods when we want to propagate some things, especially when the information needs to be propagated over a long distance. Because remember that convolution always propagates information in 1 pixel or a few pixels at a time. And if you want to propagate information over the whole image, you need something like implicit methods. So implicit methods would be writing the usual thing, but with the layer here would be yj plus 1. That will be possible, but not very practical because you'll have to solve a nonlinear equation. But we can think about something which looks like a diffusion reaction equation. And in this case, what we came up with was having something linear over here, k transpose k here, plus another nonlinear here. So this idea of having something here which looks like a diffusion because of the minus sign, and something which looks like a reaction, this is what we call 1D convolutions, is very old in mathematics. And this gives you patterns, for example, like butterfly wings or a zebra, or by the way, talking about propagation of disease, if you look at the propagation of disease over population, similar models are being used. For this kind of things, you're using what we call IMAX discretization. What you do is you have implicit and explicit. Implicit will be, this part will be the implicit one. So that's what you see in the next one. And explicit will be that particular part. And there is an inverse here, but you can do these kind of things with Fourier methods very quickly because these are convolution matrices. So these are nice things because, for example, if you needed to propagate, there's delta functions here that you barely see. And if you want to propagate them in time and just go time by time step, this is how many layers you'll need in order to get from here to here. If you naively go and said, I just want to increase my h and go with just the right to jump, you will get something like this. It will be very unfaithful to discretization. But if you use implicit method and actually invert matrices, this is how you're going to propagate forward. So these kind of network can be very interesting in order to capture information that needs to be captured on a wider range. I'm going to go quickly on this. This is where things are actually being useful, and this is an example we've prepared for this, where if you have an image, when you have, for example, this stick with two different sides, what can be, one class would be when both of them are different, and another class when they're both whites and one they're both dark. You need to see both ends of the stick in order to decide if it's going to be, if you're going to segment it as an orange, a blue, or a green. So if you're using ResNet just propagates one pixel at a time. It doesn't see both ends, and therefore it fails on this thing. But if you're using the network I just presented, the implicit network, then it sees both sides, and you can easily classify this right. Okay. I'm going to go quickly, actually, because my timing is kind of done, and I really want to talk about what we call AI in practice. So since we start working on AI, we actually start working on a lot of practical problems. And there is a lot of issues with AI that I think are worthwhile discussing in terms of, and at least being aware of, and talking about data size, data accuracy, and understanding the data. So I'm going to show you an example which we're not working on right now. This is really pioneered by Keegan, who is a student working on these things, where we were approached by people in Vancouver General Hospital to give them help in classifying information in CT images. So they're looking for these kind of structures here that are called GGOs and ground glass opacity. And there are different types of them. So one of them here looks more like a hazy thing. Here it looks more like already consolidated. And they give each one of them a different class. So there are 7 of these classes, and they want to find out what the volume of these things. And the idea is that these kind of structures appear in COVID patients, and they're much faster to, I mean, it's easy to put a patient into CT and get a response right away versus putting PCR, and PCR takes, a day, and the accuracy is about 70% is what they tell us right now. So the goal for them is to have something, it's not, you don't see the virus, but you can see things that are indicating that there is a high likelihood there is a virus. So you can do much quicker annotation here. So you start with this and you say, great, let's work on this. But you realize that there is a problem here. So first thing, there are many CT images, but not all of them are annotated, very few annotated. Typically radiologists look at them and say, yeah, I think it's COVID, but nobody really annotates it for you. That takes a lot of time and effort, and radiologists are expensive, and this is not something that we have a lot of. So that's one of the problems. You have many images, not a lot of annotated images. The data right now is heterogeneous. So we got scans from Iran, Korea, Italy, Canada, and of course the data is uncertain, which is an important point I want to demonstrate here. So the question is that GGO or not? Typically when we look at machine learning, what I call the domain expert is a 2-year-old. So CAT is diagnosed by most people. GGO, you need a radiologist, and you think this is not such a big deal here. But here is an example that we actually asked one in the beginning. We asked 16 radiologists, or here there are 12 of them, to annotate the same image. And there are different structures here, and you can see that they barely agree on anything. I mean, they agree that there is something happening in that size. But if you look, for example, they don't agree on the same type of object. So some of them agree, think that this is the right object. Some of them think that it's different thing. The shape is not the same shape. If you look at it, it's kind of in the same area, but not the same shape. So how are we going to train a network where we don't really have the ground truth, and the ground truth is not really agreed by everyone? And typically you have the ground truth. I mean, this is a particular case. We said, we were actually very persistent and said, we want all of them to do one slice so we will know at least what the variability is. I don't know any study that they do when every slice they do is done by 16 or 12 radiologists. So that is really a problem. I'm not going to answer all the questions right now. We're sending a paper about this soon, so hopefully we'll have some results. But this is something that you have to think about when you train. When you train some things. There's already, by the way, if you're interested, a web page on this with demos, and because these things, the models are already partially released and people are here working with them. But there are a lot of questions that come when you work with these kind of problems. So in practice, I really recommend that people think or rethink components. It doesn't mean you have to use immediately coarse entropy. It doesn't mean that the best way to judge your result is by looking at the IOU or whatever measures that you have to think about what's the right loss, what's the right regularization you need to use for a particular problem. So don't rush to always use existing software. There is lots of software in this field. A lot of it is very good, it doesn't mean you have to use it because the problems that you solve are not always fitting the software you want to solve. The problem with computers, they always give us answers. And sometimes these answers may be not so great. The other thing is that machine learning is working across a lot of disciplines. You really have to talk to domain experts to understand what how good your result is. Okay, I just want to conclude because Uzan is told me 45 minutes and he's going to be very aggressive if I don't do anything in time. So first thing, just kind of to reiterate that we can cast these problems as ODEs, PDE constraint optimization. The nice thing about casting things in old ways is that we have theory and we have a lot of understanding on old things. It's new science, but it's always good to link new science to old science and to understand the connection and how this is expanding. And that's really one of the tasks that we have. Now, the second thing is, when people say I'm using deep networks, to me it says I'm using PDEs. I mean, I can use, the fact I'm using PDEs doesn't mean anything because different PDEs do different things. So if you have different tasks, you're probably using a different PDE. If you're doing segmentation, you're using one type of PDE. If you're using some kind of information blurring, you're using a different one. The same thing, we should choose the PDE based on the task, and you should choose the neural network based on the task and not rush into a particular one. I presented a bunch of variability of neural networks. And again, I mean, I'm not claiming these are the only ones. There is a huge amount of research that can be done in using machinery we have developed in PDEs and in numerical PDEs towards solving and suggesting deep networks. And again, the last thing that I want to really emphasize is when you're applying deep networks into real problems, into real world problems, and not just solving a CFAR10, which we all love to solve and getting 2% better than the previous guy, then you really, really have to be careful of how you approach the problem. Rethink every component you're using. Does it fit the problem you have? And not just go ahead and say, I have a piece of software, I have data, let's just run it and everything will be just fine. Okay. And with that, I think I'm done.
Okay, thank you very much, Eldad, for a nice presentation. There are a couple of questions, so I'm going to read them through you one by one and see if you can answer them then. The first one is from Joshua Lansford, and he's asking whether this ODE treatment works only for classification or only where a linear output activation function is used for classification.
So the answer is that you can look at any network and write it like this. It's not really, it can work for anything. It's just a different way of propagating or thinking about propagating forward. Rather than thinking, if you think, I mean, the original deep network, people thought about every filter, every layer as a different filter and a discrete filter. They say this filter is extracting the face, and then this filter is extracting this. So they view it in a discrete way. In the ODE approach, you think about more as a continuous way. Each layer is doing a little bit work, not a lot of work, just a little bit more work. So you're getting a continuum at the end of the day. And I think that's the bigger thing about treating these kind of things as an ODEs or PDEs. In again, nothing in reality on the computer is an ODE or a PDE. At the end of the day, we all have layers, so we all have a finite number of layers here. It's just that the view is that when you're doing things as ODE and PDE, you think about many of them. You usually think about what happened when I have a lot of things and they're changing slowly from one to the other.
Okay. Moving on then, Joshua, if this didn't answer your question, so you can also post a follow-up question on the chat line, and I'll try to monitor it. So the next question is from Saloni Kotari, which is a bit more generic, I would say. What about loss of information?
So again, I don't know exactly what it's a very general question. I mean, so I would say again, it depends on the network you're using. Some networks will not lose information at all. I mean, you can design networks that do not lose information, that the hyperbolic networks in principle do not lose information. You can theoretically show it, you can practically see it, that whatever you start, I mean, I can go forward and I can go backward and recover exactly the same image that I have. Actually, it's one of the way we debug our codes, is doing exactly that. So again, I mean, some problems you want to lose information. Again, if I want to classify an image of a cat, I want to lose information. I don't want to have all the whiskers and the ears and everything else. I want to come eventually with, some vector of 10 in this case that tells me this is a cat. So I'm compressing information. And in some other things, when I want to do segmentation or maybe other things, I may not want to lose information. So it's really task dependent and goes to what we said about choosing the the network based on the task, not just based on the fact I'm using a neural network. So.
Okay. Going on through the questions here. The next one is from Kion Fala. You mentioned stability when the Jacobian changes slowly. Could this also be stated as requiring a small Lipschitz constant on the gradient? Are there any other connections here you could comment on?
So I think we're confusing, I'm not sure I understand the question 100%, but I think we're confusing forward and inverse. When we talk about gradient, we really think, I'm not sure if he means the gradient of the training problem or when you're doing the training.
I think it refers to the training problem.
So if it's training, that's a different thing, because Lipschitz constant on the training is one thing. We're talking just about the forward problem. We're not talking about the inverse problem at all. It's just you're asking yourself, forget the inverse problem, it doesn't exist. I'm just propagating forward. That's all I know. I don't care how I train these things right now. Is this well posed? So I think that's really that's what we're trying to answer here.
Okay. Going on, there are more questions. It is from Bamdad Hosseini. Can you allow for change of dimension in input-output using ODE PDE models or the DNNs?
So the answer is yes. There are many tricks to do these kind of things. So one of them, I'm kind of go back for a second, maybe all the way to the beginning almost. One of them, which is easy. I mean, there are tricks. This is one trick. So for example, I didn't say what the dimensions of A are, but you can think about if I start with Y and my A is not square, I can get Z to be any dimensions I want. So you can build these kind of models that do that. There are a bunch of other tricks, and we published a lot of paper. Other people have done similar things. There is with the hyperbolic networks, there are tricks that even allow you to have a pooling that is completely conservative. So for example, if you base your pooling on wavelets, so we published on this something, I know Carola published something on this as well, then you can have information that is changing dimension and also is reversible. So these kind of things can be done as well. Again, assuming that you want to change dimension to the higher. If you do it, if you just want to reduce dimension all the time, then what you'll have to do is you'll have to concatenate ODEs. So you have ODE that goes from one to the other, you'll change dimension and you go to a lower one.
Okay. And a bit along the same lines is a question from the panel, I think Benet Vidal, who's asking that the deep neural networks and CNNs are typically finite dimensional layers, obviously, whereas the PDE and ODE interpretations correspond to infinite layer limits. He wants you to comment on the gaps. That is, would asymptotic stability in the continuous time mean a network with a zero output?
So I'm hoping I understand the question right, but there are two asymptotics we can talk about. One is what happens as t goes to infinity. That's not the one we're talking about. We don't let everything go to steady state. The asymptotic we're talking about is you have more and more and more layers. So
I think he means asymptotic in the sense of going to time. But René,
can I just quickly interrupt? So René can talk actually if you wanted to.
Oh.
Yes, René, you can
which might be easier.
Yes.
Yeah.
Yes, I guess what I meant, infinitely many layers. So basically, they would provide an analysis of a network with infinitely many layers.
Mm-hmm.
And so, for example, if each layer was just a linear layer, right, you would get a linear ODE, sure. And then you get e to the AT. And so if A was asymptotically stable, then the solution of the corresponding network with infinitely many layers would just be zero always. And so there seems to be some gap in the analysis when we translate. So that's what I'm trying to understand.
No, so again, the question is, you get e to the minus TA, but that's what I asked. I mean, you're talking infinite layers or you're talking infinite time. You're talking infinite time. We're integrating to a finite time. So even if you have a linear, so e to the minus TA, A is constant, right? E to the minus TA times y0. That would be our solution. So T is constant, let's say 0 to 1, because we're all mathematicians, we integrate always from 0 to 1. We don't know anything else. That means that you're looking at the integration of 1. Now, the other stability, the other asymptotics is when you say, I'm using more and more layers to discretize the same thing. So actually, this slide that I skipped was exactly that particular thing when we did experiments on these things. When you can do continuation in the layers. So you say, I'm going to start with 2 layers, then from 2 layers, I'm going to 4 layers, and to 8 and 16 and 32 and 64, and you want to see what happens. And of course, you start from the previous solution. That's what you do in multi-grid or multi-level methods. So you can converge faster on the new layer. So this is exactly what we've done here. And what you see here, the red is what happened when you're moving from from 2 layer to 4 layer for 8 layers. The red thing is basically just continuation. The blue thing is when you're restarting from scratch. So again, you're restarting from scratch the computations. Sometimes you do a little bit better, but again, every time you start from scratch, and here is when you do continuation. And this was exactly the goal here, to show that continuing in the layer sense is better. Again, the point is not to integrate to infinity. The point is to integrate to a finite time. This is something that we do, by the way, in image classification, or sorry, in image segmentation long time ago, all the time. It's the idea behind scale space. You don't want to integrate you don't want to start with an image and do scale space and integrate to infinity, because then you usually get nothing. If you think about the heat equation, that's in the simplest form. You want to stop at a finite time that will basically get rid of the noise.
Okay. Well, we have still more questions to go, Eldad, so I guess this is a reflection of a good talk. This one is from Isha. Is there some theoretical guidelines which tells you how to solve the PDE formulation optimization problems? I assume the process of solution reflects the process of training the network. So, of course, I mean, what we're doing right now is not really amazingly different than what other people are doing in this case. Again, I mean, we're just doing the stochastic gradient descent. Maybe we have a little bit different in terms of controlling the step size and the designing the network. But I would say that we're just using literature in PDE constraint optimization, which is very similar to this. We're using stochastic gradient descent. There are attempts right now to use Newton's method, which may be doing better, but I think it's an open research area. Can we do better? Like, can we do better than stochastic gradient descent? My gut feeling is that we have to do better than stochastic gradient descent, but I'm one of the few people that don't like stochastic gradient descent. I think everybody around me loves stochastic gradient descent. I'm one of the few that hates the method. I mean, I'm kind of reluctantly dragged along the thing to admit that it works really, really well. Even though I would prefer to see something which is a higher order, or something that is more in the lines of you know, Newton, quasi-Newton, inexact Newton working here. Okay. Here's another one from Krishna. Oh, that's a complicated surname. Yeah, Krishna should be sufficient here. How about networks that have convolution kernels that are spatially, meaning of the size 1 by 1, that vary spatially, meaning of size 1 by 1, 3 by 3, or 5 and 5 by 5. And then these get concatenated at the end. What happens to the ODE PDE formulation when you have the convolutions that vary in a spatial scale? So once again, if you think about convolution as a discretization of an ODE or a PDE, let me go back to that particular slide, because I think it like this one over here. So first thing, I mean, I can, for example, say that at some point, S2 and S3 are equal to 0 at some point in time. And that means that, for example, my convolution is going to be only 1 by 1, if I look at this one. So I can change the kernel size. I can do 5 by 5. It will usually lead to higher order PDEs. Now, again, I mean, the whole point of these things, and this is something to remember, you can always interpret things as ODE and PDE. The question is, it useful? So if you're changing between each layer, it goes from 3 by 3 to 5 by 5 to 7 by 7 back to 1 by 1. Yeah, you may be able to interpret it like this, but it's not going to be useful for you, because, for example, you're not going to be able to do continuation, the process I just showed before. So again, I mean, the fact we can interpret something as an ODE or a PDE doesn't mean we have to. It's useful in some cases. It may not be useful. I don't claim that you should do it all the time. It gives you advantage if you do it in terms of building multi-level structures. For example, you can work between, right now when you work on images of 32 by 32 and you want to switch to 64 to 64, it's not clear what the convolution kernels may be. But when you're doing this kind of process, you know what they are. So again, I'm not saying that you can always interpret something, you don't have to do it. That's the only thing. Okay, there's another attendee that wants to ask. Ozan froze for me.
Okay, so now we lost Ozan, but let me quickly take over, because we had, okay, so now Sebastian, you unraised your hand. Ah, okay, you didn't want to ask a question. Okay, we had a participant who raised their hand. So Ozan, are you happy to take over again the questions? I think Sebastian just raised his hand accidentally. Yeah. Okay,
I'll continue here then. I'll go on in my list. There's another question from anonymous, we don't know the name. It's about the generalization gap. Recent works have shown that deep neural networks can be made to fit arbitrarily well relabeling of the training rate with 0 error, essentially the classical, so to say, generalization paradox. This has cast doubt on what makes one network give more generalizable solutions than others. I am curious what Eldad thinks of this problem in the context of networks being PDEs.
It's a heavy question. It's above my pay grade, as they say. I actually don't know, again, if what the approach here is helping us to generalize. I mean, stability, I think, helps us to generalize, not the PDE or stability in general. I don't have to have PDE to have stability or an ODE to have stability. It's just kind of a nice way to analyze it. But stability, I think, does help us to generalize. I do believe that we need to have stability to generalize. Now, the question is, what causes things to generalize? Recent work that we've been doing looking at generative networks is putting a lot of doubts in my mind about what's the right things and why do things sometimes generalize, sometimes not, because we're trying to understand basically a probability density function based on a few points that we're sampling from it in very, very high dimensions. How does this really work and how do we generalize? I'm not so sure about this at all. And again, some people that are much more knowledgeable than me have done papers on these things. But I think there is a big gap between the theory that we see to the practice that we see. And I think it all comes to the point that it's really, really it's really difficult to understand probabilities in high dimensions, which is what we're trying to working with here.
Okay, and I think I would close this because we are now at 5 o'clock, but by the two final questions that I have on my list. And I will actually combine them because they are roughly on the same topic. They are dealing with, again, with the choice of time point and the overfitting issue. So how would you choose the termination time point? How would it in the PDE/ODE formulation, how would it influence the prediction accuracy? And likewise, is there a characterization of overfitting in the sense that the time range of integration should correspond to the amount of layers in the network?
So the time is actually arbitrary completely. And in a second, I'll convince you that it actually should be arbitrary completely. You can say it's as long as it's finite. Of course, as mathematicians, we always say take it to 1 because 1 is an arbitrary number that is we all like. I mean, you can 2 pi, but if you really want to. But of course, it really doesn't matter because as you can see, you're multiplying h by k. So whatever you choose, eventually it will kind of go into the k. I mean, you don't even have to choose. I mean, practically, if you're using a resonant to this form, which is forward Euler, you really don't even have to do. If you're using Garnier-Kata, you need to be a little bit more careful. But if you're using forward Euler, h and k really correspond to each other. So you're training k anyway, which means you're basically training over, if you think about it, your horizon anyway. All it says, if you think what it says, that if k is larger, things are changing quicker in that 0 to 1 interval. So if I'm setting things to 0 to 1. So the larger k, things are changing quicker. It doesn't matter if it's a wave or something else that decays. So that's what happens. You don't really have to think about it that much. Unless you're using something like an implicit method, the time really plays a little bit different role here. Now, for the number of layers, the number of checkpoints on your things, really what's important here to remember is that as you increase the number of time steps, because this k is not uniform, it's changing over time, you allow yourself more variability. You think about the path. If you think about this, one of the things we had here on the path here. So if I go and replay this, replay this, there is a path that this thing is taking. In this case, it's a very convoluted path. And because we allow it to take many layers, that's the reason that it happened. If I, on the other hand, not only a few layers or all the k's were the same between them, it will kind of have to do much more. It will not have all the degrees of freedom. So having more k's or more checkpoints on more grid points in your discretization allows you to have more variability and things that can behave more crazy over time. And that's where the overfitting, of course, can come. So one of the regularization we're using, for example, I did not talk about it here, is we're using the total variation of k. So the difference between k's at different layers and the one norm of this thing to try to make these things not oscillate too wildly. We don't want k at one point to be this and the other one to be that and then do this, because then your points are moving in space in a very random type way. And they may get to the end where they want to get to, but they're not like, they're not going to move in a nice way. So.
Okay. Thank you, Eldad. I think it's time to wrap up this mini tutorial session for this talk. And well, thank you again for the time. You took time and a nice presentation. I think of course, anybody could feel free to contact you, I guess. ask for the slides and pursue the discussions as offline, where we are in some sense online anyway.
I will put the slides on my website. And again, I mean, those of you who just want to kind of have a really, really small notebook that demonstrate the idea of an ODE, there is a GitHub repository, small code that does this. And for the COVID project, there is a website that is now being demonstrated all these kinds of things as well.
Perfect. And before just closing down the meeting, I would just want to say that tomorrow at the same time, we will actually continue along this topic a bit in the sense of the connection between deep neural networks and high-dimensional parabolic PDEs by Christoph Reisinger. So you are all welcome tomorrow also, and in some sense continue this exploration of the interface between machine learning and analysis. And with this, I thank you all and enjoy, well, I would say a good afternoon, but it depends on where you're sitting, I guess. So whatever time zone you are in, a good continuation on your day.
Thank you, Uwe.
Thank you so much, Eldad. Thank you.
Bye.
Bye.